Right now, as you're watching this, a wave of solar plasma is racing toward Earth. It erupted from the Sun on July 30th, 2026, launched by a moderate M1.9 flare from an active sunspot region designated AR4492. On its own, that flare wasn't especially powerful. Flares are ranked on a scale from A through X, with each letter representing a tenfold jump in energy, and M-class sits comfortably below the most extreme X-class events. But this particular eruption was slow and long-lasting, which gave it something more important than raw flare strength. Enough time to hurl an enormous wall of solar plasma out into space, a coronal mass ejection so wide that space weather forecasters described it as a partial halo, meaning a huge portion of that material is heading directly at us. Models tracking its path put its arrival at Earth in the first hours of August 2nd, with forecasters warning of unsettled to active geomagnetic conditions and a real chance of storming reaching G2 or moderate levels. Translation. Skywatchers at higher latitudes have a genuine shot at seeing the Aurora tonight. That single event is a small current snapshot of something much bigger, and it's exactly why headlines keep insisting the sun has entered a highly active phase. Here's where we need to slow down and get the timeline right, because just entered isn't quite accurate, and the real story underneath that phrase is more interesting than the headline lets on. The sun operates on an approximately 11-year cycle, swinging between quiet stretches called solar minimum and turbulent stretches called solar maximum, driven by the slow, still not fully understood churn of its internal magnetic dynamo. We are currently living through solar cycle 25, and NASA and NOAA's joint panel of experts formally announced that this cycle reached its solar maximum back in October 2024. That means, technically, the sun didn't just start ramping up, it's been in its active phase for close to 2 years already. So why does it keep feeling like the sun is only now getting started? Because in a very real, well-documented sense, it kind of is. Solar cycles rarely peak in one clean, tidy spike and then fade away politely. Many of them, historically, show what scientists call a double peak, sometimes referred to as the Gnevyshev gap, where activity rises to an initial maximum, dips slightly, and then climbs back up to a second. Peak, sometimes months later, sometimes more than a year later, and sometimes that second peak turns out to be just as intense, or even more intense than the first. NASA's own reporting on this cycle has been explicit about it. After reaching the officially declared solar maximum in 2024, the sun has simply remained in a heightened period of activity. Ever since, refusing to taper off the way a textbook cycle description might suggest it should. And the data backs that up in a way that's hard to argue with. In early February 2026, NASA's Solar Dynamics Observatory, which watches the sun continuously from Earth orbit, recorded more than 50 separate flares in just a few days, including several X-class events, the most intense category the sun produces. Days before that stretch, a rapidly growing volatile sunspot fired off at least 18 M-class flares and 3 X-class flares within a single 24-hour window, including an X.3 eruption that stood at the time as the strongest solar flare recorded that entire year. That's not the signature of a star winding down. That's the signature of a star still actively building toward, or sitting inside, a second wave of intensity. The pattern didn't stop there. In early June, a trio of major flares erupted within 24 hours from an unstable active region, triggering radio blackouts across parts of Earth and sending multiple Earth-directed coronal mass ejections toward us, bright enough that forecasters flagged a real chance of Aurora as far south as Illinois and Oregon. Around the 4th of July weekend, the sun fired off 10 separate flares within a single day, another burst of multiple Earthbound CMEs, another round of Aurora forecasts, stretching further from the poles than usual. And now, at the start of August, that same restless pattern continues with the CME currently inbound from the July 30th eruption. A reminder that this activity hasn't been confined to a handful of dramatic weeks scattered across the year. It's been closer to a constant hum, occasionally spiking into something loud enough to make headlines, then settling back down just long enough for people to assume the excitement has passed before the next active region rotates into view. Individually, none of these events would necessarily make headlines on their own. Stacked together across a single year, they paint a picture of a star that has stayed remarkably, persistently agitated for far longer than a single clean peak would explain. This is exactly the kind of pattern that keeps solar physicists watching closely. And it's worth being precise about what watching closely actually means here, because it's not about predicting doom. It's about tracking measurable physical consequences that ripple down into infrastructure most people never think about until it stops working properly. Solar flares release bursts of X-ray and ultraviolet radiation that reach Earth in about 8 minutes, the time it takes light to cross the 93 million miles between us and the sun. That radiation can ionize the upper layers of Earth's atmosphere, which is exactly what causes the radio blackouts mentioned in that June event, degrading or completely knocking out high-frequency radio. Communication, the kind still used by aviation, maritime shipping, and emergency services, particularly over oceans and polar regions where other communication options are limited. Coronal mass ejections are a slower, separate threat entirely. Massive clouds of magnetized plasma that take 1 to 3 days to physically arrive at Earth, and when they slam into our planet's magnetic field, they can induce electrical currents strong enough to disrupt satellites, degrade GPS accuracy, and, in the most extreme cases, stress power grid infrastructure on the ground. It helps to understand why a cloud of charged particles 93 million miles away can do anything at all to a power line sitting quietly underground on Earth. When a coronal mass ejection collides with the planet's magnetic field, it doesn't need to touch anything physically to cause a problem. The collision distorts the magnetic field itself, and a distorting magnetic field, according to basic physics discovered in the 19th century, induces electrical currents in any long conductor sitting inside it. Power grids, with their hundreds of miles of transmission lines strung across entire regions, are essentially enormous accidental antennas for exactly this kind of induced current. Under normal conditions, that effect is negligible. During a severe geomagnetic storm, the induced currents can become large enough to overload transformers, some of which are custom-built, expensive, and, in a worst-case scenario, take months to replace rather than days. That's the specific, unglamorous engineering reality behind every headline warning about a solar storm threatening the power grid. It's not about a burst of fire in the sky, reaching down and striking anything. It's about geometry and induction, quietly. Stressing the same electrical infrastructure people rely on every single day without ever thinking about where the electricity actually comes from. Satellites face their own, more direct version of the problem. Beyond the induced current risk, the charged particles that arrive alongside a CME can physically degrade a satellite's electronics over time, and the storm itself can temporarily puff up Earth's upper atmosphere, increasing drag on anything orbiting low enough to feel it. That's precisely the mechanism that doomed those Starlink satellites in 2022. Not a direct hit, but extra atmospheric drag at an altitude where the satellites hadn't yet climbed high enough to escape it, pulling them back down into the atmosphere to burn up days after their launch. It's a reminder that the danger from an active sun isn't always dramatic or immediate. Sometimes it's simply a matter of bad timing, a spacecraft caught at a vulnerable altitude during a week when the sun happened to be having a particularly active stretch. None of that is hypothetical. In February 2022, a relatively modest geomagnetic disturbance was enough to destroy roughly 40 newly launched Starlink satellites, their orbits still too low, and their systems too freshly deployed to survive the added atmospheric drag a solar storm temporarily created. In May 2024, a severe G5 geomagnetic storm, the most extreme category on NOAA's scale, painted Aurora across skies as far south as Florida and northern Mexico. An extraordinary sight for most people who saw it, and also a genuine test for power grid operators and satellite controllers who spent that weekend closely monitoring systems for stress. These are the stakes underneath the Aurora photos people love sharing. The same physical process, producing a beautiful light show, is also the process capable of degrading the technology modern life quietly depends on. Which brings up the historical benchmark every solar physicist eventually mentions when this topic comes up. The Carrington event of September 1859, the most powerful geomagnetic storm ever directly recorded. It was strong enough to set telegraph systems on fire and produce aurora visible near the equator. Telegraph operators reported sparks jumping from their equipment, some strong enough to shock them. And in a few documented cases, operators found they could disconnect their batteries entirely and keep sending messages using only the current the storm itself was inducing in the wires. In 1859, the practical damage was limited mostly to that one electrified network, essentially the only piece of continent-spanning infrastructure that existed at the time. If a storm of that same magnitude struck today in a world running on satellite, navigation, digital banking infrastructure, and interconnected power grids spanning entire continents, the consequences would look nothing like a burned telegraph wire. Some estimates from engineering and insurance studies have put the potential economic cost of a modern Carrington-scale event in the trillions of dollars, with recovery. Times for the most severely affected regions measured in months rather than days, largely because of exactly the kind of custom transformer damage described above. That's the honest, non-sensational reason space weather agencies fund constant solar monitoring. Not because a Carrington-level event is expected imminently, but because nobody can currently rule one out, and the cost of being unprepared has grown enormously since the last time the sun did something like that. That uncertainty is also why solar physicists are excited about a completely different kind of recent research, one that has nothing to do with today's flare and everything to do with getting ahead of the next cycle entirely. Scientists studying the sun's long-term behavior have identified what they're calling a hidden switch-off signal buried in solar magnetic data, a signature that, if confirmed and refined, could potentially help forecast the onset of extreme space weather years in advance rather than the current handful of days. Their research suggests that extreme space weather doesn't gradually fade out as a cycle winds down the way older models assumed. Instead, it appears to end at a specific, identifiable stage, a finding that could eventually let forecasters warn satellite operators, power grid managers, and airlines years ahead of a coming quiet period, or just as usefully, years ahead of a coming active one. For now, the actual monitoring happens in something closer to real time. NASA's Solar Dynamics Observatory watches the sun in multiple wavelengths of light around the clock, tuned specifically to catch the extreme temperatures generated inside an active flare as it happens. Spacecraft like ACE and DSCOVR sit far out at a gravitationally stable point between Earth and the Sun, giving forecasters roughly 30 to 60 minutes of advance warning before an incoming CME actually slams into Earth's magnetic field. Models like the WSA Enlil simulation, the same kind of model behind this week's forecast for the July 30th eruption, take that raw data and project where a given eruption is actually headed, how fast it's moving, and how strong an impact to expect once it arrives. None of these tools can stop a solar storm. What they can do is turn a completely blind hit into a monitored, anticipated event, giving satellite operators, airlines, and grid engineers a window to brace before the plasma actually arrives. So here's the honest version of the headline, stripped of the false urgency but keeping the real story intact. The sun didn't just switch on a new active phase out of nowhere this week. It's been unusually active for nearly 2 years, ever since its officially declared solar maximum in October 2024. And instead of fading the way older models predicted, it's kept producing exactly the kind of layered, overlapping bursts of flares and coronal mass ejections that solar physicists associate with a second, sometimes stronger, peak arriving behind the first. That's what's actually happening above your head tonight, as a wall of plasma launched 2 days ago closes the final stretch of its 93 million mile journey, aiming for a planet that has built an entire modern civilization on the electronics that same plasma is capable of disturbing. There's a strange kind of comfort in knowing that so much of this is already being watched for, even if none of it can be stopped. Nobody can reach out and turn the sun down. What forecasters can do and what they're doing right now, tonight, as that CME closes in, is exactly what they did after the July 30th flare. Track it, model it, estimate its strength, and give the people who run satellites, airlines, and power grids enough lead time to brace for whatever arrives. That's a fundamentally different posture than panic. It's the same instinct that puts a weather forecaster on television before a hurricane. Makes landfall, just aim 93 million miles further out, at a star that has been quietly running the same 11-year rhythm for as long as anyone has been keeping records, and shows no real sign this cycle of settling down early. Scientists aren't watching closely because something catastrophic is guaranteed to happen. They're watching closely because after nearly 2 years of a sun that refuses to calm down on schedule, the only responsible thing left to do is keep paying attention, one flare, one coronal mass ejection, and one aurora forecast at a time.